Okay, hi guys. So in this lecture, we'll be seeing some more examples on the addition of Br2 or halogenation of alkene. So in the previous lecture, we saw some of the mechanism of we were given an alkene and we were actually passing on Br2 in presence of CCl4 or H2O, and we saw the formation of non-classical carbocation. So we'll be uh, taking on this lecture from there only. So we'll start off with example. So first example is you have to compare the rate of halogenation in this compound. So what would be the rate of halogenation for this alkene? I'm also giving the answer side by side also. Why the rate of halogenation like this? Because the formation of carbocation, which is the rate determining step, the formation of non-classical carbocation, which is the rate determining step, is in this case the formation of non-carbocation is the most stable. Hence, this would be the order. So this is rate of halogenation. Okay, so now the next question comes is I'll be giving some of the compounds, some of the alkenes, and you have to determine when they are passed on with Br2 in presence of CCl4, what would be the products, what would be the stereoisomerism of the products formed. Okay, so cis-2-butene is this when it is reacting with Br2 presence of CCl4. Carbocation, non-classical carbocation would be formed. It would be something like this, and then Br2 will be attacking on either of the carbon atom from one from up the plane and from one from down the plane. So this would be the non-classical carbocation formed, and Br minus can attack this carbon up the plane and down the plane. If it is attacking up the plane, then we will be getting something like this. This will go down the plane. Rather this thing, and this will go down the plane, and another would be something like this when Br minus actually attack down the plane. So this would be something like this. Okay, so let me draw the Fisher projection for this. So the Fisher projection for this would be uh, for this thing Br would be here, H would be here, CS3 would be here, and for this thing Br would be here, H and CS3. For this thing the Fisher projection would be actually I think in this case Br would be here. Yes, Br would be on the right hand side, H would be on the left hand side, CS3 here. This is the first carbon atom I'm talking about. Okay, so just marking it. Now in this case Br would be here, H and CS3. So can you see that they are the products formed are actually mirror images of each other, and the racing mixture is formed in which these are enantiomers. Okay, this was the first example. Let me go to the second example, wherein we have trans 2 butene. So in trans 2 butene we would have something like this and this. So when reacted with Br2 in presence of CCl4, we would get something like this. Now if Br minus attacks on the top of the plane, we will be getting something like this, in which Br comes here, this comes here, and this Br goes down. So can you see a COS and two chiral centers here? So it would be a meso compound, hence it would be something like this. So if you want to see which is going down the plane and which is going up the plane, you can simply have them here. As you have to rotate this carbon bond, so it would come something like this. Br would come on the left hand side, and this Br, on rotating this carbon down the plane, it would have something like Br would also come to the left hand side. So both Br would be here, so it would be a meso compound. If you are not able to figure it out, you can actually draw first a Sawhorse formula and then a Fisher projection. So Sawhorse formula for this case would be simply so let's say in this case for this carbon, Br is actually going down the plane. So let me write it like this. Br is going like this, CS3 is this, and H is this, and in this case Br is actually up the plane. So Br is something like this. Br is something like this, CS3 is something like this, and H is something like this. Okay, so you have to convert first this into a YY form. The YY form would be rotating this here and rotating this anti-clockwise. This both the carbon atoms anti-clockwise. So we will be getting something like CS3 as the down carbon, Br in the left hand side, H goes to the right hand side, and similarly in this case for this carbon you have to rotate it again anti-clockwise. Oh, this was the clockwise, this was the anti-clockwise. So CS3 comes down, Br comes to the left, and H comes here. Sorry. So this is the form we get. So from this we can actually make the Fisher projection from the Sawhorse projection. Okay, so I hope you are following this. Okay, so let's go on to the third example. Here we have this, and CS3 is already given above the plane. We reacted with Br2 in presence of CCl4, so we should get something like this CS3 here, one Br2 above the plane, one Br2 below the plane, and similarly here we will be getting this Br2 below the plane and this Br2 above the plane. Okay, now if you just draw a mirror across this, you will see that actually these are mirror images of each other only. Okay, so these two are actually the mirror images of each other, so these are racemic. It's a racemic mixture. Okay, so the fourth example is we have been given something like this, and Br2 CCl3. Actually my bad, I actually went on with this problem. Just a second. Yeah, this was the case in first example, and now we have this in this example. Okay, so in this example Again, the reaction mechanism, so Br will come this way in this, and if we draw a mirror, these are the two compounds formed. Okay, so if you compare these two, these are not a mirror images of each other, so we can actually remove this mirror, rather they are diastereomers. Okay, stereomers. Okay, so we have something like this, and we are again presence of CCl4 iron right. Okay, so here we'll be getting to CH2Br here. It won't be a chiral center here because two hydrogens are here, and one would be something like this, and another would be something like, please remember that there will be no optical activity from this carbon atom, so we will be directly getting these two. So at this carbon atom, if you just actually reverse it, so this would be either above the plane or below the plane. So these are the two compounds which can be formed here. So if you just look at it, this carbon bond, I should mark it as dash, and this should be wedge. So if you just look at it, just rotate it across this 180 degree in the plane, so you will find that these two are actually mirror images of each other, yet not superimposable. Obviously this is not a chiral center, but the ring is a stereogenic area, so total number of stereoisomers is n 2 to the power n. It is symmetrical. It is actually symmetrical, and it is having odd number of chiral centers, so total number of stereoisomers would be, the meso compound is 2 to the power n minus 1 by 2, and 2 to the power n minus 1 would be total number of minus 2 to the power n minus 1 by 2 is a total number of optically active compounds. So this comes out to be 0, and this comes out to be actually 1. So are we doing something wrong here, or have we applied the formula correctly, or are we doing something wrong here? According to the formula, the optically active should come out 0, and the meso compound should come out to be 1. Yes, we have done something wrong here. We cannot apply this formula because the compound is not symmetrical. If you see clearly, we have a CH2Br here. This is not a CH3, so the atoms won't actually have a plane. So let's see this carbon atom. So this has, let's say, Br here, H here, ring here, and the third H behind the plane. Okay, so if this is the plane of symmetry we are drawing, because this was the plane which we talked about, no? So if we are drawing this plane, then actually this Br has no Br on the left hand side, hence this does not qualify for a symmetric compound with a plane of symmetry. Okay, so this formulas are not valid here. You can erase them. it's a racemic mixture, it's a enantiomer. Okay, we'll see the last example after this, and then we'll be moving on to 3O and ED3O in the next chapter. Okay, so you have to basically very clear about what you are doing in each and every compound. Okay, otherwise you will land in big trouble. So just keep thinking about all these concepts whenever you are having free time, whenever you are traveling, or whenever you are with the in friends with some useless discussion is going on. You can think about all this concept. Meanwhile talking and thinking about all these things in your mind, it's perfectly fine. Means you have to keep revising your concepts in your thoughts so that it becomes rooted in your memory. Okay, what about this compound? So this would be if Br comes here, so it would be something like the carbocation formation would be there, and it would actually, we would actually have this type of compound in which if Br comes, let me draw the intermediate. So if Br comes here up the plane, we would have something like this. Br here, CH3 here, and this Br down, and this CH3 up the plane. And if this Br comes down the plane, then we would have something like this one and this one. Okay, and what if this Br actually attacks this carbon atom? Let's draw that case also. So then we would have the Br attacks this carbon atom. So we would have, and let's say it is above the plane, so we would have this one. And if this attacks below the plane, then we would have something like this one. So can you see something similar in here? This compound is actually similar to this compound, which is already covered, so we need not again draw it. And this compound is actually similar to this compound, so we again need not draw it. So only these two are formed. So now what is the relationship between these two compounds? Obviously they are enantiomers. Why? Because there are non-superimposable mirror images of each other. So because of that reason, I am ruling out that they are enantiomers. So with this we come to the end of this lecture, and from the next lecture, as I said earlier, we'll be seeing on 3O and ED3O. Okay, so till then, good luck and goodbye.